Hi, my name is Mihirpa and I'm a junior in high school, and I've developed a transformer model for predicting seagrass in Casco Bay, Maine. So, what is the research problem I'm trying to solve? Seagrass is a vital coastal plant species that has been experiencing major loss in recent years in Casco Bay, Maine. Literature has identified key stressors of this loss as light limitation, storm-driven physical damage, and nutrient enrichment. However, publicly available environmental datasets are too spatially or temporally coarse to capture these stressors and their effects on observed seagrass change. So, my objective was to build a predictive framework using the available data using a spatiotemporal transformer model to identify imminent seagrass collapse before it becomes irreversible. Now, how do I do this? Well, as ground truth, I take the seagrass polygons mapped by the Maine DEP used to classify habitat loss versus stability. As my features, I use static features such as bathymetry, slope, and coastal proximity, and I also use dynamic features such as hydrological discharge and storm parameterized sequences that include wind speed, timing, and location of storms that affected Casco Bay. I organize these dynamic features into monthly sequences to model cumulative environmental degradation trends. To use this data and build a predictive framework, I utilized a transformer architecture, chosen because of its multi-head self-attention mechanism. This mechanism dynamically weighs specific environmental timestamps in the time series data that had a huge impact on seagrass loss or no loss. Now, moving on to results. We validated the transformer model on a validation dataset with a 50-50 label split to ensure the model didn't just cheat using class imbalances in the training data. The transformer achieves an impressive area under the curve of 0.846 with a classification accuracy of 77.4%. We then also compared the transformer to other state-of-the-art machine learning architectures, including Logistic Regression, XGBoost, and LSTM, among others. As you can see in the table above, the transformer outperformed all other architectures in all metrics. This classification ability is especially impressive when considering the significant data constraints mentioned previously. We can visualize the transformer's attention weights derived from the multi-head self-attention mechanism. This will reveal which features drive its predictions. As seen on the screen, freshwater discharge receives the highest attention, with storm parameters ranking right behind them. This aligns with known impacts from ecological studies on seagrass decline. This direct link between learned weights and ecological stressors confirms our model's interpretability and ecological validity. This slide compares a subset of our transformer's predictions against observed seagrass cover changes in the validation subset. As you can see, our model accurately maps areas of loss in red and areas of stability in green, confirming that the model has a significant capability of spatially identifying imminent seagrass loss. Finally, what are the practical implications of our model? Well, by identifying high-risk vulnerability zones, the model enables proactive intervention before habitat loss occurs. Regional practitioners have already expressed interest in using these predictive outputs to prioritize targeted seed restoration. Furthermore, integrating our findings into the Cobalt Initiative's Living Atlas API provides a scalable template for data-driven seagrass protection that can be adapted to other coastal regions nationwide.